So for this video, we're gonna take a close look at the roadmap in our textbook, section 6-19. I'm using the 11th edition of the Shigley's book. And we're gonna take a look at the completely reversing simple loading right here. Right? So this serves as a guideline to solve a problem that deals with a completely reversing simple loading. And first thing, you need to determine SE prime, which is the endurance limit of the test specimen. And you can find that using this relations right here, depending if you're dealing with metric system or an English system, right? And the ultimate tensile strength of the material, SUT. So if the ultimate tensile strength of the material, let's assume it's 55 KSI, 55 is less than or equal to 100, you can use this, right? You multiply 50 times 1/2, you get 27.5, and that's your SC prime, the endurance limit of the test specimen. Then you need to modify this SC prime to determine SE. SE is the endurance limit of the actual piece you're working with. So it's governed by this equation right here. So SE is equal to Ka, Kb, Ka, Kb, right? Kc, Kd, Ke times Se prime. So for Ka, it's called the surface factor. It depends on the surface finish of the material. So the problem will state, okay, you're dealing with an AISI 1020 hot rolled shaft, let's assume. So you factor 8, you pick either 11 or 38.6, depending which system of measurement you're using, the English or the US customary units or the metric system. Pick A and you pick the exponent and you plug them back here with SUT being the ultimate tensile strength of the material. Then you find Ka, and that's your surface factor. So moving on to Kb, this is called the size factor. It depends on the dimensions of your piece. So if the shaft, let's assume we have a rotating shaft, right? We can use this. Kb is equal to this, and as you can see, it depends on the diameter of the shaft. So let's assume the diameter is 0.5. So 0.5 is larger than 0.3 and it's less than 2. Use this relation. Right, you plug in 0.5 here, you find Kb. If you're dealing with metric system, same thing. And if it's just axial, the shaft is just experiencing an axial load, right, you use Kb is equal to 1 right here, because Kc will take care of that. But don't worry for now, just Kb is equal to 1 if it's axial load. If the shaft is non-rotating or the cross section is non-circular, you have to find effective diameter, dE. You can't simply use this. If the shaft is not rotating and if it doesn't have a circular cross section, you have to find the effective diameter from table 6-3. It's in our textbook, the 11th edition of the Shigley's book. You find dE from a table. You plug it back here to one of this, and you find Kb. Right, moving on to Kc. Kc is called the load factor, so it depends on the load. If you have bending, Kc is equal to 1. If you have axial load, 0.85. Torsion, 0.59. And I think we saw this in our previous example, the one posted on the channel we had pure torsion in our problem, so we used Kc is equal to 0.59. And now for Kd, the temperature modification factor, depends on the temperature, right? Either you're using Fahrenheit or Celsius. And St is the ultimate tensile strength of the material at the operating temperature, and SRT is the ultimate tensile strength of the material at room temperature. And that's how you can find Kd, right? Moving on to the reliability factor, Ke. And this is sometimes the problem will state the reliability is 90%. You use the corresponding reliability factor, right? Ke. Okay, so now we're done with Ka, Kb, Kc, Kd, and Ke. We need to determine, oh yeah, we can find the Sc, right? The endurance limit. We found all these modification factors. We know Sc prime. Just multiply them, and then we get Sc, the endurance limit of the actual piece. So sometimes we're going to have stress concentrations, right? So for fatigue stress concentration factor, Kf or Kfs, Kfs is the fatigue stress concentration factor in shear, right? We need to find Kt or Kts first from table A15, right? Kt is the stress concentration factor and Kts is the stress concentration factor in shear. We need to find these two first and use this equation, right? If you have in shear, if it's the piece is experiencing shear, use Kfs. Right, so you might be wondering what is Q right here, or Qs. So Q is the notch sensitivity, and you can find that also from figure 6-26 or 6-27 in our textbook. But sometimes you can use this formula instead, right, to find Kf. You're given Kt, or if you're finding Kfs, you're gonna be given Kts, or you have to find Kts from table A15, right? And R is the radius of the fillet, or the geometric shape that's causing the stress concentration. So make sure you check table A15. And the square root of A can be found from this, right? If it's bending or axial, use this right here. And this depends on the ultimate tensile strength of the material, right? And if it's pure torsion, you find square root of A using this one, right? Depending which units of measurement you're using, metric or US customary unit. So once you find square root of A, you plug it back here, you find Kf or Kfs depending on the problem, and then you apply the stress concentration factor, right, to find sigma. So you multiply the stress concentration factor times the stress, you get the maximum stress. So sometimes you might have seen this before in a couple of problems where you have to find the number of cycles to failure, right, N, or the fatigue strength, SF. So the problem asks for that, and you have a completely reversing load. Remember, we're dealing with a completely reversing load, which means sigma mean is equal to 0. You find F first, this one, and it also depends on SUT. Then you come down here, you plug it to this formula, SC being the endurance limit we found of the actual piece, not SE prime. This is SE. You find A, same thing, you find B, then you come down to this equation and you plug in A and B, and if you're given the number of cycles to failure, you can find the fatigue strength. Sometimes the problem will ask you find the number of cycles to failure. It's the same thing, use this formula to find number of cycles to failure. Right, and that's basically it for a completely reversing load. Right, if we scroll up, hope you find this video to be helpful. Yeah, I hope you find this video to be helpful. It helps a lot when you're solving a fatigue problem, right? Dealing with a reversing simple load. Right, thank you. Have a good one.